All right, so my name is Juan Meza. I work at Lawrence Berkeley National Lab, where I'm the department head for the high performance computing research. Next slide, please. Mark has already done a wonderful job of introducing the subject. Let's see. All right. Maybe, maybe not. There we are. So Mark has done a wonderful job. So hopefully I will cut down on the amount of time you have to listen to me. Let's see, the computational science and engineering area is an area that Berkeley Lab has been working on for many years now. We're a Department of Energy facility, and this is one of the areas that we feel we've been doing a lot of work in for probably the last 15 or 20 odd years. Some of the lessons that we've learned from our projects have been that the flavor of the types of work that we do nowadays have become much more multidisciplinary and multi-institutional. As we go towards ever more complex codes that we're trying to use to simulate various physical phenomena or engineering phenomena, we find that we have to put together very large teams. And the teams are usually composed of people from the physical sciences, from mathematics, and from computer science. And this is really the only way to be able to tackle some of these very large, complex problems. In addition, we're finding that as you start to really get into some of the larger teams, you become multi-institutional, and in some cases you actually start to work across the borders, and so you have a lot of collaborations that are international these days. And as we do this, we're finding that the days of people writing a code for one particular application that may last a couple of years are long gone, and we're starting to shift towards community software now, where you have software that really can last for a very long time. And so nowadays we're finding that computers come and go, as we like to say, and depending on your budget, whether you're a large national lab or a small PI, you're going to change your computer probably somewhere between 18 months to 2 years to 4 or 5 years. But the codes tend to last a very long time, and so you'll have codes that can have a history of maybe 10, 15 years, and they are modified as you go along and you add more physics or math. But they outlast any one particular computer or computer architecture, and that will have implications on the types of problems that you're going to be seeing in a minute. And so what we really believe is that teraflop computing is necessary for a lot of these large problems, but it's not sufficient to be able to solve the types of problems that we're going to be looking at. So let me give you just two very quick examples as by a way of the types of things that we're trying to study. On the, let's see, is it also a triggers on the bottom?
It says advanced.
Oh no, he wants the pointer.
The pointer. It's on the bottom. I don't want to hit Kathy with it.
Do you want to use this?
Yeah. You got it. Got it? Okay. So on the far top left corner over here, you see a model of a climate model that we've been working on with the 300 kilometer resolution. And on the bottom right-hand corner, you'll see some data that was taken from some satellites. Now, something that you'll notice right away is that you have a couple of things that are a little bit messed up here. So if you're from California, for example, you'll notice that it does not rain in the winter, contrary to what we just saw this past winter. Florida is essentially a desert, as is much of Texas and the Midwest. So you start to ask yourself, so exactly what's going on in here? And we all know the answer to this is we need to have better physics and better resolution for these models. What's interesting here is that as you go to higher fidelity models, you start to capture some of the detail again. So you start to get a little bit more rain in the East Coast. The rain finally starts falling in California. And when you get down to 50 kilometer resolution, you finally start seeing some of the rain falling in the southeast that you see over here in the observations. So this is just by way of an example of here's a problem where we're looking at this, and you have to really take into account a lot of multidisciplinary codes because you have to have ocean modeling, atmospheric models, and other types of models that we haven't incorporated yet. Another example I'd like to point to here is because this one involves a lot of foreign collaborations, is that recently we found out that, essentially we have 95% of the known universe is made up of unknown stuff, dark matter and dark energy. And to look at this, we have several collaborations here, of which I just note a few. And let me give you one example here where we had a particular simulation done for cosmic microwave background radiation. Here, the point I'm trying to make is that this was the first time we've ever been able to do a first full year resolution for both the intensity and the polarization for a data from the what will go up in 2007, the Planck satellite. We had to use 6,000 processors, 4 terabytes of memory, and 2.5 terabytes of disk. But it did map for the first time what we believe will be a one-year simulation data coming down from the satellites, which will be on the order of about 75 billion observations. So this gives you a trend of where we're going with these types of things. So to do these types of problems, we've developed a strategy which involves using simulation and modeling for a lot of different variety of applications. I've talked about the climate modeling and the high-energy nuclear experiments. But I didn't get a chance to talk about nanoscience or genomes to life. Teresa will probably talk a little bit about the computational biology stuff. And we're also doing some work with combustion processes. The point that Mark was making was that a lot of these problems now require modeling and simulation as a third leg of the science that we're trying to accomplish. So to do that, we believe there's 4 major areas, and hopefully we'll be able to talk about this during the panel. You need to be able to take a look at the computer architecture and try to develop new computer architectures that are really suitable for the types of applications that are coming down the line. This gets to one of the questions that was asked just a minute ago, so why people don't like to have clusters. Part of the answer is, the straight answer is, we don't like to share. So that's part of it. That's societal. But the other part of it is also it's very, very hard to try to find a particular computer architecture that's applicable or optimized for every individual application. So that may have some truth to that. We'll see. Another thing that we're finding, another trend, is that data management and visualization is becoming a much more important area to take a look at. This is twofold. One is, as the models become finer, for example, in the climate modeling, the data sets become larger. As the data is streaming down from satellites, we have higher resolution, we have a lot more data that we have to analyze. Both cases, we're talking about terabytes or even petabytes worth of data, and we need to try to understand what's happening, not just collecting the data. So those are 2 areas that we need to take a look at. And then the 2 other areas that we really want to be taking a look at is the applied mathematics and scientific computing. There's a very well-known graph that shows that you get a certain amount of increase and speed up from computer architectures, but in fact, algorithms and modeling and the mathematics have been giving us as much power as about 15 or 20 years worth of computer architecture. So we really need to be able to focus on new developments and new algorithms to be able to really fully take advantage of the types of problems we're going to be looking at. Finally, because of the fact that this is becoming multidisciplinary, multi-institutional, you need to be able to have the systems that are distributed and people can collaborate over very wide areas. So for example, in the cosmic microwave background radiation, people at CERN and people in the United States need to be able to collaborate very easily. So those are areas that we need to be taking a look at. Multi-scale modeling and cybersecurity are 2 topics that we're looking at very carefully. And finally, just to finish up, this is the building that Mark was alluding to. It will house NERSC, a $38 million facility funded by DOE. The plan, hopefully, is to have collaborations, very close collaborations with both UC Berkeley and other UC campuses, wherever people are interested in collaborating with us. Just to give you an idea of the building, it's going to have about 140,000 square feet of area and about 360 spaces for staff, not all of which will be just lab people. Hopefully we'll be able to get people from other universities to come and sit with us and be able to collaborate with us. So with that, I'll finish.